Welcome everyone to our next Go Fly Master Lecture in the Master Lecture series. As everyone knows, we're so pleased to have Boeing as our grand sponsor of the Go Fly Prize. We are joined by corporate sponsor Pratt & Whitney, as well as over 20 aerospace and STEM organizations around the world. It is my pleasure to introduce Greg Bowles today. He is the Vice President of Global Innovation and Policy for the General Aviation Manufacturers Association, or GAMA, which is responsible for the identification of key technological opportunities to evolve the global safety, efficiency, and success of aviation. Greg leads the GAMA Electric Propulsion and Innovation Committee, which represents the world's leading aviation mobility development companies, along with traditional aviation manufacturers, as this community strives to enable new kinds of public transportation through the air. Greg also currently leads the Worldwide Design Standards Committee, which is chartered to develop globally accessible means of compliance for general aviation aircraft. Prior to joining GAMA, Greg worked as a certification engineer at Keystone Helicopter and was a design engineer at Cessna Aircraft Company. Greg holds a Bachelor of Science degree in Aerospace Engineering from Embry-Riddle and an MBA degree from Webster University. He is an active instrument-rated general aviation pilot. Thank you so much, Greg, for joining us.
Hey, thank you for having me. I'm excited to do this today.
Greg, it looks like we lost your video.
I think we just lost it. I'm sorry.
That's okay.
And all things fall this way. I'll be right back, I think.
No problem.
See if it jumps back on here. I guess launching again.
There we go.
Okay. Okay. Would you like me to share my materials?
Absolutely.
Okay, perfect. So I will get that going right now. And thanks for having me do this. Is that working? You're seeing?
So it looks like we just want to put it in full screen mode. It's in presentation mode right now.
Got it. I'll switch monitors on. Better?
There we go. Looks good. And if you want to just adjust your camera, perfect. Thank you.
Perfect. All right. So, so thanks for letting me talk to everybody. And as you mentioned, my name is Greg Bowles. I'm with GAMA, and we've been working in this space for about 5 or 6 years to help enable new types of aircraft. What I'm hoping to walk you through this morning is actually a little bit of background about where aviation has been, general aviation specifically, around the globe, where we sit at the moment, and why we're so excited about what's happening in the hybrid electric and the increased automation space, and where we think that's going. If there are questions and thoughts about the regulatory environment, I think that's an area we have a lot of expertise, and also the global market questions. So feel free to ask those towards the end. When I discuss general aviation, what I am talking about, what we kind of moniker general aviation as, is this stuff. So we talk about business jets, turboprops, piston airplanes. General aviation to us means everything except for the commercial airlines and the military. So it's a big segment. When we look at traditional general aviation, what's in that mix, in the world, most of the aircraft in the sky are actually small piston airplanes. That's most of what exists. the slice that most of society is very familiar with, where most people interface with aviation today, is that little blue slice, commercial airliners. And there's a lot more going on, obviously, but it doesn't affect our lives on a daily basis. We interact mostly through commercial flight. That has a huge potential to change. We're going to talk about 60% of aviation products exist in the US, a quarter in Europe, and then there's a distribution around the world. We're seeing growth in those segments. So those new segments are growing. We're seeing a lot of growth in Asia. We're seeing a lot of growth in South America. And so over time, we imagine the balance of aviation distribution will kind of grow towards those areas. But it's not that we're dividing the pie differently. It's actually a growing pie, right? We're growing aviation in those areas more quickly than we are others. If we look at that slice that we talked about, that little segment of piston aircraft, or that big segment actually, those products are pretty old. So this slide here can show you when they were produced. The heyday of aircraft production was back in the 70s and 80s. And today, the average aircraft in the sky is over 50 years old. So I just talked to a group of folks this morning about some of this, and you know, there are not a lot of industries that mark themselves as roaring successes with an average asset of 50 years old, unless maybe you're like some kind of collecting industry, maybe stamp collection or something. Here's another data point for us to look at. GA tower operations. So this is, we call it itinerant operations. So this means aircraft coming or going from an airport, not doing touch and goes, but leaving and coming from the airport environment. So if we look at that from 94 to 2000, we don't see anything remarkable. It's just, you know, data. At that time, the FAA predicted that segment would grow around 3%. In reality, over the next three or 4 years, the segment declined, and the FAA again said we'll see 3% growth starting now. And cutting to the chase here, in reality, what we saw was continued decline in GA operations, and every year the FAA would predict more activity, but in fact, it actually continued to decline. So here's another data point to kind of level set where we are in the traditional aviation world. Looking back at the average age of pilots in 1966, when I look at this as an engineer, I say that's a good distribution. I have young folks that are taking up flying in the middle of age. We have the peak of people in the activity, and then as older folks move on to other things, they kind of end their flying career. And so we've plotted this year to year to kind of show you how that's evolved since the 60s. And you can kind of see as it starts moving. After Vietnam, we had the GI Bill, and we had a large chunk of pilots come online. And then the next interesting thing happening here, look at this, 60 to 64, lots and lots of folks, and this actually spills over. There it goes. The FAA does a reaccounting, and our older pilot population continues to grow. And as we kind of move down the path here towards 2015, last year we had really good data, you can see some numbers that aren't as inspiring. So we have that group of GI Bill pilots that are just continuing to push up against that line where they don't continue to fly anymore, and there's a big gap in young folks taking on flying. So you kind of wonder, what is it about flying that's not attracting people anymore? There's some good studies, but in general, the facts are that there are other alternatives to spend your time. Flying takes a lot of effort to get into. It takes a lot of effort to be safe and current. The training process and the licensing process hasn't really kept hasn't kept pace with modern times. And the products we talked about, the average product out there is 50 years old. So if a young person has this inspiration to fly, and we take them out to the airport and we start telling them about a carburetor and showing them a 1965 perfectly beautiful Cessna, it's not necessarily what they were envisioning. So I think a lot of the work that's going on in the GoFly team to reinvent aviation from a certain perspective is really valuable and important to pull in young people and to make aviation much more a mainstream part of life. I'll talk about this a bit more. So another data point I wanted to bring to everybody to help us with some thoughts. I'm showing you that count. This is a raw count of accidents, and then the orange line is the fatal accidents every year in general aviation. One of the things that we do that we have to be cautious of, we let that accident number, that big accident number on top, hide that orange line underneath. So I am one of the belief that accidents are important, but fatal accidents are really what we have to focus on. And what I'll do is draw a parallel to the car world. So if I'm in my car and we have an accident, if somebody bumps into my car in the parking lot at a store somewhere and they do some damage, I'm not going to get upset at Ford or GM. It's just a bad day, and that day gets better in a few days. But if that accident happens and people are severely injured or it's a fatal accident, it's unacceptable. And so we need to really focus on those kind of things. In aviation, if we take a deep dive look at those fatal accidents, well, first, this chart that I'm showing you shows that fatal accidents are very, very robust. So as an engineer, that trend is persistence. We have not made a lot of impact on that. Now, why not? Let's take a look quickly at where those accidents are coming from to understand them better. So this is work that was done by something called a group called the GAJSC, the GA Joint Steering Committee. And what they did is took a deep dive look at accidents, fatal accidents, between 2008 and 2015. Excuse me. And the first column here you see is loss of control. So these are stall spin type accidents, and we'll take a little bit of a deeper look here in a second at those. The second category is control flight into terrain accidents, and we'll also look at that a bit more. Third is systems and component power plant, so that's power plant failures. And the fourth cause of fatal accidents in general aviation is actually running out of gas, fuel accidents. So running out of fuel is the fourth cause of fatal accidents in GA. That's a bit of a shocking thing to think about, that in today's day and age, people are still running out of fuel, and it's causing that many fatal accidents. Just as important as understanding what are the most prevalent fatal issues is understanding what's not. Often we see regulators and we see folks focusing in areas to try to make improvements and spending a lot of resources. Right here, for example, if you look at icing, so there has been efforts to improve the regulatory landscape for icing. And one of the things that, we want to make things as safe as possible, no question. But spending a lot of time and resources on icing, if you look at this chart, will give you about a 0% improvement in safety. So we can be totally successful, make aircraft that are totally protected from icing forever, and not make any meaningful impact in safety. So this data is really important to use as a baseline as we kind of look at where aviation should go and how we should improve the products and even think about future products. So let's talk a little bit about that loss of control accident. So that big column, the first one, the most important one to focus on, loss of control, what's happening? Most of these accidents are occurring in the traffic pattern or around the airport during daytime VFR, nice weather, and they're happening from the base to final turn and right after departure. And they're a classic stall spin accident. In this scenario, we're low energy around the airport and we're down low to the ground. So we're low potential and kinetic energy, and that's where stall spins are most dangerous. Now, we're taught as pilots from the first get-go to recognize slow flight. We're taught how to avoid the stall spin accidents. And the fact is that humans are fallible. So what makes us wonderful is that we don't always do what we're told. We can think outside the box. We can bring experiences from other parts of life and save the day often when we're flying in ways that we weren't necessarily taught. And that also is our fallibility. So while we often do this just right, on rare occasion, we don't. We stall spin. And as engineers, we can look at this and say, well, that's a pilot problem. Or we can look at this challenge and say, how do we make humans better and be able to focus on what humans are good at, that X factor kind of thing and that on the loop kind of thinking, and we take some of the in the loop activities away from the human so that we don't have these fallibility mistakes. So let me show you a bit more about how we've done that in some areas. So if we look back at this chart of accidents, the number 2 accident, that's controlled flight into terrain, crashing into terrain we didn't know was there, basically mountains, trees, rising terrain. So in the past, when you were using a paper chart and you had your VORs or you were doing NDB navigation, it was, you know, a lot of mental calculation and potential for error. This chart here shows the hourly data related to CFIT. So control, flight, and terrain on an hourly basis began declining in 2005, and it continued. There wasn't a new rule. There was no new training. What came online was actually technology. So handheld GPS, the iPad, installed displays started to come online as well, and it had a tremendous impact on safety. So this is an example of where the human calculation in the mind was error prone, and it was a high task environment, high likelihood of making mistakes, fixed by technology. Because this was carry-on technology, it was low cost and easy to be employed. That's not necessarily the case for control, flight, and terrain. I can't think of a carry-on piece of equipment that would really have a silver bullet kind of impact there. But there are installations we can do. So we'll talk about that in a second. If we look at fatal GA accidents, the ones I've highlighted here are the human error aspect. So, you know, human error is a key issue that we need to look at. And so we've started doing some work at GAMA to try to address that. So the first thing that's needed, the regulations themselves classically were very, very detailed. And if you wanted to do anything different than the regulations, the Part 23 regulations are for designing airplanes. So classically, if you wanted to do anything different, that's airplanes up to 19 passengers and 19,000 pounds. If you wanted to do anything different than that big stack of paper classically, you had to get an exemption. So an exemption is a possibility. It takes quite a bit of time. It's a lot of effort. And traditionally, this is not something that startups engaged in. They would, it drove a lot of people away from the game. And these rules were based in old technology, old designs. And if you wanted to do anything modern, you had to get an exemption. We were able to work with the FAA over the last 10 years, and we actually worked globally with regulators around the world to change that regulatory environment. So that 377 regulations became 71 high-level performance-based or objective-based regulations. So instead of telling somebody how to design a dynamic seat so that it will have a certain amount of deflection during the test and what the test parameters will look like and how much seat cushion compression there should be, instead of that test that's about 6 pages in detail, the new rule says that you need to protect the occupant in the event of a crash near stall speed. And so one means of compliance, so there are means of compliance that exist in standards now. One means of compliance is to do that old seat test. Other means of compliance are to design rigid structures to include airbag seatbelts, to include lower stall speeds, to build crumple zones. So all these new options now exist in standards that can be dynamically built over time. So where the old process was, I have a good idea, and the rules prevented it, and you had to get an exemption if you really had the fortitude. The new process is, I have an idea, well, it fits the rules because the rules are high-level objective-based now. And to develop a means of compliance, you can either propose your own and have the FAA accept it, or you can develop a consensus standard. And we have formed an industry group called ASTM F44, General Aviation Aircraft, for that kind of forum. And that's where we sit with other engineers and other designers, and we talk about areas we need new paths for compliance for things as I just described, like crashworthiness. We're working on all kinds of new paths: electric propulsion, cybersecurity, indirect flight controls, which is like another way for saying fly-by-wire. So we're working on all new standards that are much more well suited for the lighter segments of aviation. So not extremely expensive solutions. So the way I illustrate this for the uninitiated, so we used to have these rules over there, which says historic Part 23. The white lines were the concepts that were contained in the rule, and it had all this orange detail that was based in the 1950s and 60s technology of the day. So what we've done now is we've kept all the intent. The intent of those rules is what remains in the new rules. So the safety objective or the intent is still in Part 23. And we didn't throw away all those histories and detail learnings on how to apply this to specific technologies. What we've done is we've moved all that to standards, And then we built new standards. So over time, we've added additional material for modern technology. So instead of just having the means of compliance that we use for carburetors, we now have means of compliance for all kinds of new technology like electric propulsion, as I mentioned. So this effort was a global effort that we went under, and I was lucky enough to kind of champion this. In 2013, that's a picture of Obama signing the Small Airplane Revitalization Act of 2013, which pressed the U.S. on towards getting this across the line. The rules completed here in the U.S., the rule right completed in 2017. And so today we're 2 years into this environment, and standards are continuing to be built for all the new technologies. We also worked with the EASA. I actually lived in Brussels for several years to work with the European authorities to help get a similar set of rules across the line in Europe in the spring of 2017. Right now in China, in Canada, and New Zealand, Australia, all around the world, the regulators are moving towards this framework of rules, and we are all using the identical means of compliance. So today, the world sits around the table at ASTM F44, and in that environment, we develop new means of compliance that can be used. So the goal is you can do something once, and the world's regulators will accept it instead of having different environments at the detail level around the world. So it's a very, very powerful tool. It's a really great collaboration area. So we work with key folks, and it's been a pleasure for me. I chair this activity and got it kicked off about 5 years ago. And it's been an absolute pleasure. Really smart folks from around the world. Our next meeting will be in April in Brussels. It's the last week in April, and it's an open forum for those who want to come. Actually, on the Tuesday, the last Tuesday of April this year, I think it might be the 22nd or 23rd, something like that. We're going to be holding a forum on eVTOL technologies, and we're going to be talking about new means of compliance that we're developing, such as inadvertent icing for eVTOL. We're going to be talking about some of the cyber standards, some of the crashworthiness standards for eVTOL, some of the electric charging standards, and materials that need to be developed for the next year so that we have new means of compliance. So at GAMA, we began with a small group of companies back in 2015 discussing where we wanted to go. And today, around the table, we now have 79 companies. So these are the groups that are around the table here at GAMA, working in the hybrid electric and eVTOL space to develop new rules, new regulations, ways to operate these aircraft in airspace in key markets around the world. There were predictions back in 2017 that the eVTOL market would be a $35 billion market. And then recently, Morgan Stanley put out a really bold prediction that $1.5 trillion market, which is pretty drastic change in 2 years from a prediction standpoint. What I will say about the technologies that we're seeing, hybrid electric, the reason I kind of pivoted fully towards this and GAMA has paid a lot of attention, we do think this is a disruptive change. And so this is a slide I show a lot of folks about what that can mean. So if you look at what's circled there, that's Easter morning in New York City on Fifth Avenue in 1900. And that's a car, it's an automobile or a car circled with a whole bunch of horse and buggies on the street in New York City. And then 13 years later, this is Fifth Avenue, and we've circled the only horse and buggy on the street. So in 13 short years, the world changed, right? So certainly societies have changed based on that technology. And we think that hybrid electric propulsion, simplified operation, and eVTOL will have a very similar effect. We've seen like a microcosm of this kind of thing happen before. I've got for you an illustration of what happened with glass cockpits in aviation. So when Aviation came along in 2003 with the first glass cockpit in the Cirrus, you can see in about 2 or 3 years that technology swept everything in aviation. And today, all aviation cockpits are integrated glass. It's a pretty minor step compared to what we're talking about with hybrid electric and eVTOL, but it's an example. So we began our efforts at GAMA with focus on the hybrid electric propulsion, and we looked at battery safety, electric propulsion integration. At that time, the means of compliance and the regulatory environment for aviation using electric propulsion looked like this. There was a little bit of hope for some really light stuff in Europe, And there was, we knew that the idea of this Part 23 update was coming online in the FAA system at that time, and so we had some hope. So the two little glimmering spots of hope in 2015. Over the years, the Part 23 effort became more real. So in 2016, we knew that key regulators were really engaging more. And then by today, you can see this is today's regulatory environment. So we think that there is a pretty strong possibility to use and certify this equipment in Europe, and the US is moving along pretty quickly as well. And then the other key authorities around the world are quickly moving. So in just 3 or 4 years, the regulatory scope has really grown to embrace this new technology. If we had been discussing this 10 years prior, I would argue that most of this would still be red. The regulators had not really been ready to evolve in the classic sense, but we were able to really get some excitement in the regulator world, and we've seen them embrace these technologies in really smart ways. Doesn't at all mean our work is done. These are challenging environments that need a lot of work on a day-to-day basis, but we're seeing some really great work at policy level to enable this stuff. So another piece I'll talk about quickly here is simplified vehicle operation. So we talked about the classic accidents, and I wanted to kind of walk through the traditional state of automation. So we would traditionally have an autopilot, and that autopilot is functioning well when it has all these various pieces of information that it cross-checks. And what we've done historically is we never want to have any misleading data. So anytime there's a miscompare, so I might have multiple sources of heading, multiple sources of altitude, anytime there's a disagreement, what we do is we shut things down. So for example, if we had a miscompare in heading information, we would shut down the automation, and we would hand the aircraft back to the pilot at that time and say, okay, something's gone wrong. I know you haven't been flying this aircraft for a while, but we're going to let you take over while things aren't working so well. So that's kind of the state of traditional automation. And we're starting to look towards systems that don't go offline when miscompares happen, but maybe perform more resiliently, maybe fail more resiliently. So an example of that might be like a redundant flight control computer system. But even with this, traditionally what we've done is we've defaulted to basic flight modes when we have miscompares. What's being looked at now would be something like this. So if we had a bad piece of heading information, using redundant architecture of kind of lower cost, lower integrity devices, but many of them, we might flag, hey, we have a known piece of bad information. So maybe we'll flag that to the pilot and say, you got a piece of bad information in the heading system, something went wrong, got a maintenance action for you, but nothing shuts down, right? So to the pilot, things other than maybe a potential maintenance action to check out some heading information, the resilience gets us there. So with this kind of approach, we call this the era of simplified vehicle operation. So we went from the federated cockpit, the round dial glass cockpit, to integrated cockpits with the glass, as we talked about a minute ago. And we're moving towards simplified cockpits and eventually front row seats. So I'm going to quickly talk about simplified cockpits, and then we'll have time for questions if that works. As we move down this down this path, what happens is the real heavy workload, the mental processing that we have to do, that mental picture that we have to draw to understand where the aircraft is, to manipulate flight controls, keep the aircraft stable and on course, that starts to taper down, and humans are able to spend time, we pilots are able to spend time doing the stuff we're really good at as humans, the on-route stuff, the mental, the thinking, the making decisions, the stuff that our executive functioning is really good at, because we're out of the weeds in some of that detailed workload. But that means we move towards increased automation. So to help some of the regulators around the world understand these concepts and why they're maybe not so scary, we started to say, what is a pilot? So when I assume this pilot is flawless, we put them in there, we have them manipulate the controls. What allows that person to do it? We take a person who has a desire to fly, we give them some written study material, we put some software, if you will, in their head, and then we give them some flying experience, some more mental software, and then we do a medical check to make sure that their physical processing of the controls, and they're going to remain cognizant to do that. It's possible, and then we let them do it, right? So this is how we make this person that's able to connect all the controls in the cockpit. And so as an engineer, if we drew a parallel, we sometimes call that person, that pilot is like a meat processor. So instead of a computer processor, he's a organic processor sitting there with the knowledge of flying in their head, the software that we were programmed with. And so we start to say, okay, now if I were to replace some of what that pilot did, some of the functions with computer processor and software, is there a smarter way to do it? We started to work down this path called the deconstructed pilot. So what I'm showing you here is the key functions that a pilot performs in the entry-level scenario of piloting. So we took some of the basic flying skills and chapters of coursework and broke them into areas that we train pilots in. And so from an engineering perspective, we can kind of look at these as functions that might be able to be automated end-to-end. So instead of saying we do everything here, we could look at discretely at one function. So let's look at navigation, for example. If we look at the job of automating navigation, I think most of us are pretty comfortable with that idea. Today's navigation systems are very robust. They're better than me. So if you put me in a field that I've never been to and say, Greg, where are you? I probably won't be able to tell you if I haven't been there before. I might be able to look at the sun, know what time it is, and give you a sense about what direction is north and south and east and west, but that's probably the best I'll do. Or I'll tell you it's hot and I know it's winter, so it must be in the southern hemisphere. But you know, with computer automation, it's a simple mental leap to say, yeah, we can automate navigation. Similarly, other things on this page are not so easy. Maybe communication might be a little more difficult. So because we use so much verbal communication in aviation, having systems understand what humans are saying to each other and the intent behind that's a little more of a leap and a little more work to get to. But by looking at these functions and considering from an end-to-end perspective, could we automate some of these functions? It makes an interesting question. Could we have a pilot rating that where the aircraft took on some of these functions and the pilot shared some of these functions? So maybe I have an aircraft where half of these things are required by the pilot, and maybe that abbreviates what it takes to be current and safe and to do flight training by quite a bit. And so this is a path that we're working with regulators around the world on right now. And it's the first time we've really tried to take work off of the shoulders of the pilot in a regulatory sense. So classically, we put equipment on and we continue to add requirements. We add training requirements every time new equipment comes on. And the goal here would be to add new equipment in ways that actually allows us to take off the responsibility, to make it easier to be a pilot, to have less recurrent training, less licensing requirements. And so we're going down a very interesting path at the moment. eVTOL is obviously something we're working very, very heavily in. And I think the last slide I'll share before we go to questions here, within GAMA, our electric propulsion and innovation subcommittee and our subcommittees are structured such that we're working through the details of these issues on a daily basis. We meet several times a month all over the world with hundreds of folks and regulators on these issues. And this is the construct of how GAMA is doing that. So within the ethics, the parent committee, we're talking about these issues at a high level, and then we have a focus on simplified vehicle operation, a focus on electric propulsion, focus on eVTOL, a focus on infrastructure for these new aircraft and designs. And we're just about to actually stand up a new datacom committee to talk about new data link paths, like how to utilize 5G in aviation, how to utilize maybe the car-based DSRC links, maybe some paths for non-proprietary aviation links that will enable new things as well. So I think Needy and Dan, I appreciate the chance, and I will take a pause with that.
Great. Thank you so much, Greg. Really appreciate all of the information provided. A few questions that we've got. Let's see. The pilot shortage that you mentioned is addressed by autonomy. Is full autonomy required, or does some automation help the pilot pool as well?
So we think that everything we do, it's not automation. The automation would be the end state, but simply modernizing pilots is going to bring folks into our industry. So, you know, if we move from the average product being 50 years old to the average product being 10 years old, I think that would attract a lot of new people to being interested in the industry. I think the last few scenarios I just discussed with respect to simplified operation. So you can imagine if you had to do half as many things to become and maintain your skills as a pilot, that would bring in a larger chunk of the population. It would mean it would be cheaper to be a pilot. It would mean it would be less effort and work to retain safety and currency. So all those things are really important in the positive direction. So what we're talking about here is going from what's an unhealthy cycle, where we have an aging pilot population, aging products, which is getting less and less interesting, to turning that cycle around the other way, right? So now we're talking about bringing new products online, making it easier to be a pilot, bringing more people in to share and have discussions, and taking this thing in a healthy circular direction. So, so that's the beginning, and I think the work that's happening at GoFly is critical to really sparking that kind of positive environment.
Yeah, absolutely. It seems that certified autonomy is not nearly as close as originally claimed. Do other new trends that will enable UAM, so for example, electric propulsion, multi-rotor, ADS-B, Internet of Things, microelectronics, help with the pilot shortage issue in the meantime?
So I'll say two things about that. One, absolutely. So in the meantime, I think all these technologies do add to making this a healthier environment. I think it makes it safer, it makes it more interesting, it makes it more attractive and less burdensome. I also think that there's a strong willingness to take on pretty significant levels of automation to the level of autonomy in aviation. When we talk to folks from the road world, the car world, they will kind of look at our air challenges and say that we have it easy. We don't have pedestrians stepping out in front of our airplanes in the sky anyway. And so our challenges our time frames are slower. So the rate at which things happen in flight is much, much slower. We're not talking microseconds. We're talking typically minutes for decision making. Rarely few seconds are important. And so, you know, our time frames are much, much more possible for automation. So as a result, we're starting to see FAA, we're seeing other regulators look at limited ability to do automation. So one concept that's being looked at real heavily is the idea of letters of authorization for tubes of airspace, where you might be given the ability to be the dispatch. So your company might dispatch and control that tube of airspace, and if the FAA needs it back, and this would be an already controlled airspace, for example. So you can imagine in like the footprint of Class B airspace, you might be given a tube where instead of going through air traffic control, you're responsible. It's not VFR, it's not IFR, it's just airspace that you're dispatching in. And remaining in that tube is possible, and if the FAA needs it back, they can make a phone call and say, you need to be on the ground, and you're not using your tube at that time. So these walk and crawl and walk approaches are coming online now for automation and autonomy. And I imagine we're going to do a lot of our learning in that kind of safe environment and really see things expedite in the coming years.
Great. You also mentioned safety issues that result from timely pilot action or inaction, and suggest that technology can help the pilot, you know, for example, envelope warning or envelope limiting. These technologies are not new and are already available on modern aircraft. How is the UAM excitement related? And if so, what is keeping these technologies from more widespread application?
So it's true that we do see some fly-by-wire solutions today that protect the envelope of the aircraft. The two issues that really are holding them back, number one, they're extremely expensive, weighty, and burdensome solutions that are unaffordable in most of the lighter end of aviation. And then the other piece is that they're actually not full-time solutions. So we can look at some recent accidents and accidents in the past and see that when we see these kind of miscompares, we shut down that automation, and then we have outcomes that we don't want. So I think that we're looking at the next stage beyond that. We're looking at using potentially less robust systems and components, but in architectures that make them much more robust overall. So the system solution might be 3 or 4 pieces of airborne electronic hardware that are slightly different from one another, that back each other up in ways that give you a much more robust system overall. So I think this kind of thinking is based on what we've seen, and moving in this direction, we're starting to see a lot of new lighter aircraft companies take on envelope protection, take on fly-by-wire systems, or I guess we're calling it indirect flight control systems that allow us to do the stability augmentation to fly eVTOL aircraft, which wasn't possible just a couple years back.
Greg, you had also mentioned, obviously, you are familiar with our GoFly teams and the stage that they're in currently in the development of their personal flying devices. And you mentioned your expertise and knowledge, certainly at GAMA, around regulatory issues. And I wonder if there's any advice that you can provide to our GoFly teams at this point as they're approaching this new regulatory landscape and what they should be thinking about, who they different agencies that they need to be looking into, research they should be doing, and that sort of thing.
So one of the things that always seems to be an issue is really, really good engineering practice gets us a long way. Sometimes the regulations don't line up with really, really good engineering practice, and understanding where those gaps exist early is important. There are 2 ways about it. Often, if there's a gap and it doesn't make sense to do something, you can work with a regulator to be able to do what's right. Sometimes, because of having to blend into the environment with other aircraft or other reasons, you need to be able to conform to the rule as it was written at some point in time. And having to redesign for that at the last minute is a real problem. So early recognition that there are serious regulations out there that need to be understood is key. I would suggest folks put the regulatory work in parallel with the early design work and get a good understanding, and that way it doesn't become an obstacle for you. And then the other piece of this is early work with the regulators. Are key policy folks at the FAA and EASA and other regulators around the world now who are very interested in being helpful. And so by sitting down with them early and having these conversations, you can identify what might be some of these really problematic spots, and you can really limit what is potentially going to be a difficult situation.
Great. And any tips in terms of how teams should be reaching out to these regulators at the FAA or other agencies that you mentioned around the world, or how they should be thinking about these conversations, what they should be bringing to the table when they're looking to have these conversations?
So I think it would be smart to engage at the FAA. There's a group called the Policy and Innovation Office at the FAA. And so I think that those folks are extremely open to having conversations with applicants like the GoFly teams. And I can certainly provide some contact information needed to use so you can distribute that, and we can get those regulators to sit down and have very friendly, helpful conversations early on. In Europe, we see similar work happening with EASA. We've been visiting with the CAAC, the Chinese authority, recently, and we're seeing a very similar attitude. Some of the regulators around the world are less mature, where they're trying to figure out things for themselves a bit. And often the more mature authorities like EASA or FAA are willing to go sit down with applicants and those new authorities or growing authorities to help them along too. So certainly from the GAMA perspective, we're always open to lending a helping hand to new and growing companies, and I can provide some resources so your teams can have those conversations.
That would be great. Perhaps, Greg, we can be in touch with you and offer a resource that our teams can reach out to at GAMA, who might be able to provide some guidance for our teams as well, if that's okay with you.
Absolutely, we'd love to do that, yeah.
Great, perfect. Another question we have coming in is, how are you going to prevent the unregulated use of very cheap human-carrying drones, which is likely to mirror the current widespread unregulated use of model drones?
So we've had some conversations about some of this, and we've drawn the parallel to, in cities, we're seeing a lot of the scooters. So, you know, the electric scooters that are around and caught cities off guard. All of a sudden, there's a lot of pedestrians that are now on electric wheel vehicles, and I guess hospital rooms are starting to see a lot of head trauma and broken ankles as a result. And so the question is, do air scooters become a thing, right? This is kind of the question. In the U.S. system, you wouldn't be able to do any flying of a vehicle like that without permissive regulation. So it would be against the law to do anything like that without fitting into a regulatory construct. So there is some activity happening in the ultralight segment. We're starting to see some very light electric vehicles there. And I think the FAA is taking some serious look at when people are on board, what's acceptable for rental and what's acceptable for commercial use. What are the over people policies? And historically, the regulators have kind of looked at a level of risk. If an individual wants to put themselves at risk to do something exciting in aviation, like skydiving or something to that effect, the regulator will allow it as long as that person understands what they're getting into. But if that person wants to hold more people at risk, maybe go over top of people or take more people with them, they hold things to a higher level and a higher bar. I think that the U.S. system is laid out in a way that that will continue, and the regulators are evaluating that appropriate level of risk across those products right now. We're seeing similar things happen in Europe. We just had a conversation, as I said, with about CAC, and I know that they're having those conversations in China. So absolutely, the drone world really helped the regulator understand what's happening, and I think we're pivoting in that direction.
So Greg, that's all of the questions we have right now, but we really look forward to providing some additional resources that you mentioned at the FAA, at EASA, and certainly at GAMA as well. So thank you so much for all of this information, and we look forward to continuing our partnership with the GoFly teams.
Thank you very much, Nidhi. I appreciate it. It was good to talk to everybody.
Take care. Bye-bye.